record. I hope this works. Okay. Let me just say, we're fine. Okay, so today we are covering Chapter 8. And Chapter 8 is all about hypothesis testing. Okay? So the idea behind hypothesis testing, okay, is that we have a question or a claim about the population. Okay. And we want to investigate this question or claim. But of course, just like everything else, we cannot observe the population directly. The population is too big to be observed directly. Okay? This is the central problem of statistics, is that the population is too big to be observed directly. Okay. And so our question is the population, so it could be, here's an example question. Example questions or claims to investigate. We'll say, is the population of the United States %50 female? Okay, that's one possible question. All right, or we could say, does 21% of adults, or not does, do 21% of U.S. adults smoke cigarettes? Okay, these are the types of questions where we want to answer. Okay, now notice that in these questions there's a value. Okay, there's a value in the question. We're asking, is the population 50% female, or do 21% of U.S. adults smoke cigarettes? Okay, the question we're asking isn't what percentage of adults smoke cigarettes or what percentage of the population is female. Okay, when you're doing hypothesis testing, there is a specific value in your question or in your claim that you are testing. Okay. Questions have a specific value that we are testing. Okay, so there's a question or claim about the population. Again, the population is too big to be observed directly. Okay, so what we do is we observe a sample. Okay, and based on what we see in the sample, we make a conclusion about the population. Okay, so again, the in every scenario in statistical inference, we have a population. It's a big thing. We cannot observe it directly, so from that population we take a little piece out. This is called our sample, and we study the sample, and assuming that our sample is random or is a representative sample of the population, we make conclusions about the population based on this sample. Okay? So let's say we were trying to answer this first question. Is the population of the U.S. 50% female? Okay? And let's say, so we take a random sample of adults in the U.S. or people in the U.S., and let's say our sample looks like this, okay? So let's say our sample, we looked at 200 people, and let's say the number of females is 104, okay? What is 104 out of 200? Yeah, so 104 is 52% female. This is the proportion that shows up in my sample, okay? So if this is a random sample that's supposed to be representative of the United States, or should be representative of the United States, it's a random sample, remember that. And in our random sample, we observe 52% female. Does that mean the population of the U.S. is not 50% female? What do you guys think? You guys?
When you say it's not 50% female, you mean not exactly 50%?
Yeah, exactly 50% female. Okay. So, well, okay, the question of exactly is...
You mean precisely 50% is what I mean.
Okay, so if we counted every single person in the United States, and we counted every single female in the United States, it will probably not be exactly 50%, okay? But in order, how many people are we going to have to look at to get that, okay? So the question here is just basically, when I see a sample like this, is this enough for me to say that in the United States we don't have 50% female, we have a number other than 50% female?
Yes.
Yes? No? What do you guys think? Are you comfortable then to say we have more than 50% female in the United States?
Yes.
Based on this sample?
No.
No. Okay, so my sample is showing more than 50% of the United States is female, but basically we're asking, okay, do we have more than 50% female in the United States? And basically, I think our intuition says, well, your sample only has 200 people in it, and 52% isn't that different from 50%. So I'm going to say I don't have anything to disprove or say no to this question. Does that kind of agree with how your gut instinct here? Kind of? Do you even understand what I'm saying here?
Totally lost.
You're totally lost. Okay. So, well, what we want to know is, someone says, okay, so someone claims the United States is 50% female, okay? 50% female. And you say, well, I'm not sure if I believe that. Someone else says, it's more than 50% female. There's more than half of the people in the U.S. are female, okay? So one guy says it's 50% female. Someone says, no, there's more, okay? So you go out and you take 200, you select 200 random people, okay? And when you select 200 random people, you get 104 are females. And so you get a sample that's 52% female. So based on this, are you going to side with this person that says the U.S. is 50% female, or are you going to side with the person that says the U.S. is more than 50% female? Or are you going to say, well, I don't know. We're gonna say either way. Either way. Is this making more sense? So maybe someone's suggesting new policy, right? They're saying someone says, you know what? Over 50% of the United States is female, so when we build our next school, let's make sure we have more bathrooms for females than males, okay? And this is, we're going to write a new law. All buildings that serve both men and women need to have more female bathrooms because the United States is more than 50% female. All right. I mean, this is ridiculous, right? But just imagine we're going in this direction. So you need to decide, well, do we have evidence that the U.S. is more than 50% female or not, okay? And so you go through and you take a survey. You select 200 people, and you get 104 females. 52% are female. Is this convincing enough to say, okay, let's go with this? Why is it not convincing? Yeah, because basically the only difference between a sample that would have been 50% female and 52% female when you're looking at 200 people are these 4 additional females here, right? And this is a randomly selected sample. So if somebody else had taken a sample of 200 people, is it quite possible that they got 98 females rather than 104?
Yes.
Yeah, okay. So when we see something like this, okay, all right, our gut instinct tells us that, okay, it is not exactly 50% female, okay? But the sample is not huge. And 52% is not significantly different from 50%. I'm so sorry that I'm running out of space here. Let's see. What do I do? Is not significantly different.
Professor?
Yeah.
What does it say after the sample is not?
Hang on. Is not huge. Is not huge, okay? Significantly. Okay. So the sample that we observe is not 50% female. It's not 50% female. But the sample isn't that big, only 200 people, and 52% doesn't seem significantly different from 50%. Okay? That's what our gut is telling us. Right? Okay. So we'll save that. Or do I need to go back? Everybody got this written down? Okay. So we'll continue on here. And on the other hand, okay, let's say there was a past study. Okay, so second example. Okay, so in a past study, and it was found that 21% of adults smoke cigarettes. Okay, I'm making up this number. I don't know if that's accurate or not. Okay, but let's just say in a past study it was found that 21% of adults smoke cigarettes, okay? And let's say somebody, I don't know, created a public service campaign, okay, against smoking, okay? So there's a campaign against smoking goes on the air. It goes on for, I don't know, let's say a year, okay? Campaign against smoking goes on for a year. Okay? And they want to know, was this campaign successful? Okay? So we want to know if the proportion today after the campaign is less than 21% adults. That's basically what we want to know, okay? So the question that we have, do less or fewer than 21% of adults smoke cigarettes after the campaign? Okay. All right, so let's say, and this is our data, you took a random sample of 10,000 adults, okay, and in the random sample, only 19% of adults smoke. Okay? So this is your random sample. Does this mean, does it seem like the percentage of adults who smoke, is this significantly different from 21%?
No.
Maybe, maybe not. Okay, so the question is, is 19% significantly different oops, there's an extra L there. Significantly different from 21%? That's the question that we have. It's 19% significantly different from 21%, but this time we're not looking at a random sample of 200. We're looking at a random sample of 10,000 adults. Okay, so what do you guys think?
Yeah, from that sample says it's a difference of 2,000 people.
Yeah, it's a pretty big difference, right? So 21% out of 2,000, or it's 200 people. 21% out of 10,000 is 2,100, and 19% out of 10,000 is 1,900. So we have basically a drop of 200 people. Now, could that drop be accounted for just by random sampling? Or is it telling that maybe something changed in the population? This is the question that we're asking, okay? So there's two possibilities, okay? To answer this, is 19% significantly different from 21%, okay? So if our sample is 19% of adults smoke, our sample basically has what? 1,900 smokers out of 10,000 total, right? Total people. Okay. But again, this was taken by random sampling. So there's two possible answers to this question. Okay. Is 19% significantly different from 21%? One possible answer is no. 19% is not significantly different. From 21%. Okay. Our sample is only 19% smokers, or has only 19% smokers, but that drop, or that difference, is a result of the random sampling process. Okay, so that's one possible explanation. Okay, they're saying whenever you take a random sample of people, in this case we took a random sample of 10,000 people, whenever you take a random sample, you're not going to get the exact same results. And one possible answer is that our sample only had 19%, and that's just a result of the random sampling process. Every time you take a random sample, you get something different. We just happen to get 19% from random chance. That's what one claim is. Okay? And the other claim, or the other possible answer to is 19% significantly different from 21%? That would be yes. Okay? 19% is significantly different. Different from 21%. Okay. Random sampling can explain part of the difference. May explain part of the difference. Oops. But the 2% drop is too big to be explained by random chance alone. Okay, so the proportion or the percent that smoke in the population is less than 21%. That's the other possible explanation. Okay. And those are pretty much the only two possible outcomes. And we'll look at our data to see which one is a better, explains things a little bit better. Okay. Do we understand what these choices mean? Okay. So when we look at a random sample and it doesn't look exactly the way we might think it should look, okay, if in the past we found that 21% of adults smoke cigarettes, we take a random sample, we're expecting our random sample to also be about 21% smokers. When we see that it's 19%, we have to ask, well, could it be 19% just because of random sampling? Or does this actually mean that our population has changed? Okay, so that's what hypothesis testing tries to answer. Okay, we try to answer these questions by looking at data and seeing what they say about the population. All right, so when we do hypothesis testing, we always set up something called, there's always a pair of hypotheses, okay? So for hypothesis testing, we always have a pair of hypotheses. Okay. One is called the null hypothesis. And we write that H0 or HO. And then the other is called the alternative hypothesis. And we write HA. Okay. The hypotheses are always about the population. Okay, so when we are dealing with proportions, the hypotheses will always have P, okay? We'll always use P and never P hat, okay? Because P is for the population, P hat is always for a sample, right? So the hypotheses are always about the population. So when dealing with proportions, they will always use P, and they will never use P hat, okay? And another hint, okay, or another thing to help us out is that the null hypothesis will always have an equal sign. The null hypothesis will always have an equal sign, and then the alternative hypotheses will always have greater than or less than or not equal to, okay? Depending on how the question is written. Yeah, so we'll go over all of this, okay? So I'll walk you through an example here, okay? So the hypotheses, basically when you come to the conclusion for a hypothesis, you're either going to choose to reject the null hypothesis or you choose not to reject the null hypothesis, okay? So it's kind of like having a criminal trial, okay? So imagine a criminal trial. Okay. And in the criminal trial, we have a pair of hypotheses. One is that the defendant is innocent. And the alternative is that the defendant is guilty. Okay. So is innocent of the charges or is guilty of the charges presented against him or her. Okay. Now, in our system of law, what do we say? We always presume that the defendant is innocent until proven guilty, right? So we assume innocence until the defendant is proven guilty, okay? So we assume innocent until proven guilty. Okay? And so it's the prosecution's job to present enough evidence to convince the judge or the jury that the defendant is guilty. If the prosecution doesn't have enough evidence, what happens? They drop the case, right? The judge will dismiss the case or whatever, okay? And then even after all the evidence has been presented, then the jury has to decide, was this evidence enough to convince me that the defendant is guilty? Okay? And what are the decisions that the jury makes? The two verdicts that they can come to are what? Guilty or not guilty, right? Does the jury ever make a decision of innocent? Does the jury ever say, we, the jury, find the defendant innocent? No, okay? The jury always says, we, the jury, find the defendant guilty, or we, the jury, find the defendant not guilty, okay? And that is because they set up these, essentially our court system has set up the hypotheses in this manner, okay? There's either enough evidence or enough data to convince the jury beyond a reasonable doubt that the defendant is guilty, or there isn't enough, and they have to conclude that the defendant is not guilty. A not guilty verdict does not mean the defendant is innocent. It just means there wasn't enough to convince the jury that this person was guilty. Okay? So we assume innocent until proven guilty, and the decisions are guilty, which is or not guilty. Okay? And those are the only two possible decisions. Okay. So when it comes to hypothesis testing, we have something similar. Okay? You have a null hypothesis and you have an alternative hypothesis. Okay? And the decisions for a hypothesis test are either reject the null or do not reject the null. Okay? You never say accept the null. Okay? That would be like saying found innocent. Okay? So the defendant is either found guilty or not guilty, and our decisions for a hypothesis test are either to reject the null or not to reject the null. Okay? So that's important. Just keep that in mind. You're either going to reject the null or you don't reject the null. So how do we decide whether to reject the null or not reject the null? Or do you need to go back? Okay. 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 Is everyone good? You're good? Okay. So how do we decide to reject or not reject the null? Okay. Again, these are the only two decisions. We either reject the null or we don't reject the null. And how do we decide? Well, the decision is based on probability. Okay. We're going to assume that the null hypothesis is true. Okay? It's in the same way, like for a court case, you assume that the defendant is innocent. Okay? You assume that the null hypothesis is true. Okay? Then you look at the data or you look at the evidence. You look at the data and we ask, if the null hypothesis is true, how likely are we to observe the data that we have? Okay? And so if it turns out, if it is highly unlikely for you to end up with this data, then you would reject the null hypothesis. Okay. On the other hand, if it is likely to end up with the data, even when you assume the null hypothesis is true, then you do not reject the null hypothesis. And this is how we make our decisions. So what does this all mean? Okay, so let me just bring it back to the criminal trial, okay? Did anybody listen to the Serial podcast? Yeah. Okay, some of us. Okay, well, anyway, in the Serial podcast, there was a guy, he was convicted of this woman's murder. But the podcast, the premise is, should this guy have been convicted? How strong was the case against him? Okay. And basically, they go through the evidence, and they start to question these things. If we're to assume that the defendant is innocent, how likely is it that his cell phone records show that he was near the scene of the crime? Okay, is it possible that he was innocent and for his cell phone to ping a tower near the scene of the crime? And so let's just say that was one piece of evidence, okay? And you have to ask, okay, well, if we assume that this person is innocent, how probable is it for a cell phone to ping a tower near the scene of the crime? Likely, unlikely, and we have to decide, okay? And if that was the only piece of evidence, okay, then what would you conclude? You'd say, well, it's probably not enough to convince me that this person is guilty. If that was the only piece of evidence, you would say, it's probably not enough to convince me that this person is guilty because he could be innocent and he could have just happened to be passing through or whatever, for whatever reason, and his phone pinged the tower, okay? And let me just take an aside. Let's say this is not the serial case, but this is some other murder case. Maybe the evidence in this other case is much stronger. Maybe not only did the cell phone ping a tower near the scene of the crime, maybe I don't know, tire tracks from the car were found that matched the defendant's vehicle. Tire tracks from the scene of the crime matched the defendant's vehicle. We'll say fibers from the crime scene matched the defendant's clothing, okay? And now we have to ask another question. Okay, if we assume that the defendant is innocent, how likely is it for matching fibers to appear, matching tire tracks to appear, and a cell phone tower to be pinged? And the jury has to decide, okay? And hopefully there's enough expert witnesses to provide some good background here. But the jury has to decide, okay, well, if the guy's innocent, I suppose someone else with matching, whatever is possible. Or maybe the experts say, these fibers only appear in, whatever, these things. And so it's very, very unlikely that somebody else happened to have matching fibers and matching tire tracks or something, right? If they say, oh, these tires are the most common tires in the world, you can find, 50% of the nation have tires that match these tire tracks, you'd say, oh, well, could have been anybody, okay? And they say, these fibers, these are super common fibers, these are just your standard Hanes t-shirt fibers that show up everywhere. If that was the case, you'd say, oh, well, I guess it's possible that somebody else happened to have matching tires and matching fibers, okay? But if the expert testifies, oh, you know what? These tire tracks are very rare, okay? They were only produced in this time, and only a few cars in the nation have these types of tires. And these fibers, also very rare. And it's I haven't seen fibers like this in any kind of garment, and I'm surprised that we found them at this scene of the crime and on the defendant, okay? And if that was the evidence, well then you'd say, oh, well, that would be a lot more compelling to say the defendant is guilty, okay? So you have to balance and say, well, is it likely, is it quite possible for the data or the evidence to appear if the guy was innocent? And if it's quite possible, then you'd say, oh, well, I'm not convinced that he's guilty, okay? It doesn't prove his innocence, but it just says, well, I'm not convinced that he's guilty. On the other hand, if it's incredibly unlikely for the evidence to appear, if we were assuming him to be innocent, then you would say, well, I cannot accept that this just happened by random coincidence, and you conclude that the guy is guilty. In the same way, we're looking at our data, and we're going to say, how likely are we to end up with this data if the null hypothesis were true versus it not being true? Conceptually, does this make sense? Yes, kind of. Some people are shaking their hands. Okay. Well, maybe we'll try an example here. Okay. Okay. So let's say we have. You guys ever go to Vegas? You were just there. Did you win? Or did you lose? A little bit? You came out ahead? Or
Yeah.
oh, okay.
Can you
That's,
count cards, Professor?
I can count cards, but I cannot play.
Get away with it.
Cannot play. No. I can't count cards well. Okay, so no. The answer is no. Anyway, let's say you play. This is a very crude roulette board. Okay, roulette wheel. All right, you guys know roulette? Okay, you spin the wheel. Okay, some of these things are red, some of these are black. Okay, and let's say, well, in America, the casinos stick it to you, and 18 out of the 38 are red. Okay, so let's say you're taking a friend, and he just wants to play roulette. Okay, and he just wants to say he's just going to bet on red every single time. That is his strategy. Okay, so the probability he wins any one game is 18 out of 38. Okay, or the probability of a win, 18 divided by 38, 40.4737. Is that okay? All right, and so this is a game of chance. What happened in the past doesn't matter, okay? You go to any roulette table, they tell you the past numbers that hit, okay? And it's as if that would influence your bets. And it does. You're like, oh, well, it's hit black a bunch of times, so red is bound to come up or something. That's not how it works, but the casinos understand the poor decision-making abilities of the human brain, and they take advantage of that, and they give you free alcoholic beverages to enhance your decision-making ability. And so, well, anyway, you're there to have a good time, right? So let's say you bet on roulette on red every single time, and let's say you play 200 games. You've got deep pockets, all right? Play 200 games, and let's say you win 49% of the games. Okay? And then somebody comes out, the pit boss, he's like, man, you won 49% of the games, and according to the rules of probability, you should only be winning 47% of the games. I think you're doing something funny, and that's why you're winning. What would you say?
It's only 2%.
You'd say, well, I didn't win that much more, okay? I just happened to get a little bit lucky, okay? All right, so somebody accuses you of cheating. They say, this is what they say. According to probability, you should win only 0.4737 of the time. You won 0.49 of the time. I think you are cheating. I just imagine some dystopian future where a robot comes out and says these things to you. You are hereby charged. RoboCop. RoboCop at the casino. That would make a good movie. Those of you in Hollywood, let me know if you decide to go with that. All right. Okay, so let's say this happens. Okay, well, can we figure out the probability of winning 49% of the time or more if the probability of winning is 0.4737? Let me change this question, okay? Let's say you play 200 random games. The probability of winning, this is exactly what the scenario we're facing. Probability of winning is 0.4737. And I'm asking, what is the probability that in 200 games you win 0.49 or more? Do we know how to answer that? We should. You guys just took a quiz on it. All right, so let's let me copy this, and we'll start a new slide here. Okay. Okay, so let's answer this. Okay, so what do we have? We have n is equal to, we need n, and we have p, and we have x or p hat. What is n? 200. What is p? 0.4737. And what is our p hat? 0.49. Okay? Good. And we want to know what's the probability of getting 0.49 or more. Okay? Well, my standard error is going to be, what's my standard error? 0.4737 times 1 minus 0.4737 over 200. Good. So let's pull out the calculator and we'll do this. Oh, look, I have that. So I'm going to just do that times 1 minus that. This is 0.4737 divided by 200. And I'm going to take the square root of that. And I get 0.0353. Okay. And so my z-score is going to be, what is my z-score? Yeah, so p hat minus p over the standard error. So that would be 0.49 minus 0.4737 divided by 0.0353. And so my z-score, 0.49 minus 0.4737 divided by 0.037. I get 0.46, a z-score of 0.46. Are you guys with me so far? Okay, what's the next step I do? I look this up in the chart. So I look up 0.46, and I get 0.6772. Okay, so the area to the left in the chart is 0.6772. Is that my answer?
Nope.
No, what do? I do 1 minus that, okay? 1 minus 0.6772. Why am I doing 1 minus? Because it's saying 0.49 or more. Okay, so 1 minus that gives me 0.3228.
So 32.3%.
Yeah, so we'll just say 32%, okay? What is the probability that you win 0.49 or more? We'll just say, yeah, 0.3228. That is our answer. All right, what was... So going back, okay, someone says, you should win only 0.47 or 47% of the time, and you won 49% of the time. I think you're cheating. And so you say, no, I just happened to get a little lucky. And in fact, it's not that weird that I won 49% of the time. Because if somebody plays 200 games, the probability that they win 49% of the time or more is about 32%. Okay? So 32% of people who play the game 200 times will win 49% or more. So it's not that weird that you won 49% of the time. Okay? Does this mean the person is innocent of cheating? No, it just means he didn't play enough to convince you that he's cheating, okay? So what this says is that a person who plays fairly plays 200 games fairly will win 49% of the games about 32% of the time. Okay? So, in other words, it happens quite frequently. So, this is not convincing evidence that he is cheating. Okay. Is that okay? Let me do one more thing and then we'll take a break. Okay? Just want to make sure you guys have everything written down. What's that?
Just a second.
Okay. We'll do one more slide, and then we'll take a break, and then we'll finish up. You guys ready to move on? Just a second, okay. Good? Okay. All right, let's say on the other hand, someone else, you go to another casino, you play 200 games of roulette again. Again, still the probability of winning by betting on red is 0.4737. Okay. Okay. So let's say someone plays 200 games of roulette and they won 70% of the games. Or let's not go so extreme. We'll say 65% of the games. Yeah, that's still a little. I don't even want to say 65. I'm gonna just change it. I apologize. You're gonna win 60% of the games. Okay? They win 60% of the games. So someone says, "I think you're cheating." Okay? We ask, "Is this evidence that the player is cheating?" Okay, so we don't know what's happening, okay? But basically, if somebody plays 200 games, what's the probability that someone playing fairly will win 60% of the games? That's what we want to know. Okay? So, again, the casino manager says, or the pit boss says, hey, according to the rules of probability, you should only win 47% of the time, or 0.4737% of the time. You've won 60% of the games, so I think you're cheating. Okay? The guy might say, no, I'm not cheating. I just got really, really lucky. Okay? I just happened to get really lucky. Do you believe him?
No.
Maybe, maybe not. Okay. Well, so the guy's defense is saying, no, I just got lucky. Okay? So when accused of cheating, the defense, I just got lucky. All right? I'm not doing anything shady. All right? I just got lucky. So we're going to say, okay, well, for argument's sake, let's assume you were just really lucky. Okay? And we're going to say, if you played fairly, if somebody played 200 games fairly, what's the probability that they will win 60% of the games or more? That's what we want to know. If someone plays fairly, what's the probability? If someone plays 200 games fairly, what's the probability that they will win 60% of the games or more? Let's do it. All right. You guys want to try this on your own? Okay, go.